Dear children, let us continue the lesson Magnetic Effect of Electric Current. In that, let us study the concept electromagnetic induction. We have already studied that current carrying wire causes a magnet to move. That means current carrying wire causes magnetic compass needle to deflect. Hence, current carrying wire creates a magnetic field around it. So, current carrying wire, around a current carrying wire, there is a magnetic field. After that, later we had studied about a current carrying wire. When it is kept in a magnetic field, it experiences a force, and that force which was experienced, the direction of that force was studied with the help of Fleming's left hand rule. Now, in this class, we are going to learn that we can produce current by moving conducting wire inside a fixed magnetic field or keeping conductor fixed and changing magnetic field. So, this is called as electromagnetic induction. Okay. So, Michael Faraday, the English scientist, was the first person to prove that a magnet can create a current. To test this, he moved a magnet towards and away from the coil of wire which was connected to a galvanometer, which you can see in this picture. So, the Michael Faraday, with the help of a coil, he used a magnet. He moved the magnet in and away by connecting it to the galvanometer. So, what is galvanometer? This galvanometer is a device which is used to detect a current. So, galvanometer is a device which detects the presence of current in the circuit. So, if there is no current, there is no deflection. That means the pointer remains at 0. If the current flows in the circuit, then it deflects either to left or towards the right. And this galvanometer symbol, it is denoted in a circuit with the help of a symbol capital G. Okay. So this galvanometer is used by Michael Faraday, and he observed that there was a deflection in the galvanometer indicating that a current is induced in it. So what is induced current then? So induced current means a current which is obtained due to the relative motion between the coil and the magnet. Okay, the current which is obtained due to the relative motion between the coil and the magnet is called as induced current. This induced current means current which is produced by movement of wire in presence of the magnetic field. Okay, so now let us study how this current is induced. So this phenomena was called as electromagnetic induction. So that means the production of electricity from magnetism is called as electromagnetic induction. So current can be produced either by moving conducting wire inside a fixed magnetic field or keeping conductor fixed and changing magnetic field. So this was discovered by Michael Faraday by his experiment, which had led to the discovery of electric generator, okay, which supplies electricity. So Faraday arrived at few conclusions by moving a bar magnet in and out of the coil of a wire. So let us see some of the experiments which was performed by Michael Faraday, okay, and let us go through it. So the first experiment was motion of a magnet with respect to a coil which produced induced current. This was done, and this activity was done. So what was done? If a magnet is moved towards or away from the coil of wire connected to the galvanometer. So what happened? The galvanometer was showing the deflection when the current was induced. So this shows that current is induced in the coil due to the motion of the magnet. So when the magnet is moved in and out, so what happens? There is a current which is induced in this coil. Okay. So inside this coil the current is induced and it is detected with the help of a galvanometer. So let us see how the current is induced and in which direction the current is induced depending on the motion of the magnet. You can see here when the where the magnet is moved inside where the north pole is inserted into the coil, that time you can see the direction deflection of the galvanometer, and in the same way when it is moved out the direction is towards the right side. So let us observe this picture now. So here when the magnet moves into the coil, the galvanometer deflects towards the right side. In the same way, when the magnet is kept stationary, what happens? There is no deflection, showing that there is no current induced. So when there is no motion between the magnet and the coil, when it is stationary, then the current is not induced. When the magnet moves out of the coil, when the magnet is moved out of the coil, what happens? There is a induced current, which is the galvanometer shows the deflection towards the left. So when the magnet is moved in, the galvanometer shows the deflection towards right. When the magnet is moved out, the galvanometer shows the deflection towards the left. And when the coil is kept the coil is not stationary now, the magnet is stationary and the coil is moved in and out. So during this condition, what happens? The galvanometer deflects to right, which indicates that the current is induced in this case also. So when the coil or a magnet is moved in and out, when there is a motion in between the coil and the magnet, the current is induced in the conductor. And when it is stationary, when there is no motion, relative motion between the coil and the conductor, when there is no relative motion between the magnet and the conductor, there is no current induced, so the galvanometer does not show any deflection. So this relative motion between the coil and the magnet produces a current. So Faraday made the following three conclusions by his experiment. So the conclusion was that a current flows in the coil only when there is a relative motion between the coil and the magnet. So if there is no relative motion, if the magnet is kept stationary, the galvanometer does not show any deflection, showing that there is no current induced. So when there is a relative motion, what happens? The galvanometer connected to the coil shows the deflection. This was the first observation made by Michael Faraday. The second conclusion was that the direction of deflection in the galvanometer is reversed if the direction of motion of the conductor is reversed. So here the direction of the deflection in the galvanometer was reversed when the polarity of the magnet was reversed. So by inserting the north pole or by inserting the south pole, the direction of the induced current also gets reversed. Okay. So the third conclusion was that the current in the coil is increased. That means deflection in the coil, deflection in the galvanometer was increased by rapid motion of the magnet. When the magnet was moved in and out very fast, the time the deflection was more, which indicates that current in the coil is increased. And by using a strong magnet, so when we use a strong magnet, there the current induced is increased. Next, the third conclusion was that by increasing the area and number of turns in the coil, as the area of the coil was increased or as the number of turns in the coil was increased, the current induced was more. So these were the three conclusions made by Faraday by his first activity. Later, he had performed another activity in which the moving magnet is replaced by a current carrying coil, and the current in the coil was varied. So change in magnetic field produces induced current. So here the magnetic field was changed. by changing the varying the current. So you can see this activity here. So for that, two coils was taken, two coils of wire which was wound around a cylindrical paper roll, and it was one connected. The coil First coil was connected to a battery and the other coil was connected to the galvanometer. So you can see there is a distance here between the coil 1 and coil 2, and you can observe here the number of turns is more, here the number of turns is less. Okay. So if the current is passed through the first coil, when the current is passed through the first coil with the help of a battery, what happened? The galvanometer needle shows a deflection in the second coil. So what it means, if the current is disconnected, the needle, there was no deflection. Okay. And when it was disconnected, the needle moves in the opposite direction. What it shows that the current is induced in the second coil due to the change in the magnetic field. So from this above observation, so in this activity, we observe that as soon as the current in the coil 1 reaches either a steady value or 0, the galvanometer in the coil 2 shows no deflection, right? So from this observation, we conclude that here the potential difference is induced. The potential difference or current is induced in the coil 2 whenever electric current through the coil 1 is changing. Okay, so coil 1 is called the primary coil and the coil 2 is called the secondary coil here. So as the current in the first coil changes, the magnetic field associated with it all changes. Thus the magnetic field lines around the secondary coil also changes. Hence the change in this magnetic field lines associated with the secondary coil is the cause of magnetic field in a conductor, which induces a current in the another conductor. Okay, so this process by which a changing magnetic field in a conductor induces a current in another conductor is called as electromagnetic induction. Yes, so this process, this phenomena is called as electromagnetic induction. So current is induced in both the above activity. So this phenomenon is called as electromagnetic induction. So we can define electromagnetic induction as the phenomenon by which electromotive force or current is induced in a conductor due to change in magnetic field. So when there is a change in magnetic field near the conductor, what happens? Current is induced in the conductor. This phenomenon is known as electromagnetic induction. So in both these above activities, which was this experiment which was done by Michael Faraday, he concluded that due to in electromagnetic induction, what happens? The moving wire in a when it is kept in a magnetic field or changing magnetic field keeping wire fixed, in both this case the current is induced. Okay, so we can define electromagnetic induction as the phenomenon by which electromotive force or current is induced in a conductor due to change in magnetic field near the conductor is known as electromagnetic induction. Okay, so but how to find the direction of induced current? We find direction of the induced current by using Fleming's right hand rule. So in which direction the current is induced is our question now. So to find this, we are using Fleming's right hand rule. Okay, so the direction of this induced current in the coil is given by Fleming's right hand rule. So what Fleming's right hand rule states? So when we stretch the thumb, forefinger and the middle finger of the right hand so that they are perpendicular to each other. So when it is perpendicular to each other, that means each finger should be 90 degree perpendicular to each other, as you can see in the figure here. So if the forefinger indicates the direction of magnetic field, this is the forefinger, it indicates the direction of magnetic field. If the forefinger indicates the direction of magnetic field, thumb shows the direction of the motion of the conductor, then the middle finger will show the direction of induced current. You can see the middle finger which shows the direction of the induced current. So this rule is called as Fleming's right hand rule. So what the Fleming's right hand rule states, when we stretch thumb, forefinger and the middle finger of the right hand so that they are perpendicular to each other, if the forefinger indicates the direction of magnetic field and the motion of the thumb indicates the direction of motion of a conductor, then the middle finger shows the direction of the induced current. So this is how the direction of the induced current is found with the help of Fleming's right hand rule. So now let us see, already I have studied now, I have told how the current potential difference is induced in the coil when the magnet is moved. So you can see here, just observe, the magnet is moved in and out. So due to varying magnetic field, the current is induced, right? So you can see here the current is induced. You can see how the current is induced with the help of this voltmeter. Potential difference is found out with the help of this voltmeter, showing that there is a potential difference which is induced. So here you can see there are only 5 turns. So the current induced is less. If we increase the number of turns, what happens? The potential difference will be more, showing that the current is been increased with the help of increasing the number of turns. Okay. So if we increase the speed of the magnet, then also the current induced increases. So this is how the activity was done by Michael Faraday. So now to understand it, now see this video, we'll clearly understand about how this current is induced in the coil. Just watch this video.
Electromagnetic induction. Prepare a circular coil out of copper wire. Connect the two ends of this coil to the two terminals of a sensitive galvanometer with the scale having 0 at the center. This closed circuit is shown in the diagram. Note that this circuit contains no source of electricity and the galvanometer shows 0 reading initially. Take a bar magnet NS and move it swiftly towards the coil with its north pole facing the coil. You will observe a deflection in the galvanometer when the magnet is moving. The deflection indicates that current is set up in the coil. Now, move the magnet away from the coil. The galvanometer shows again a deflection, but in the opposite direction. This means current is set up in the opposite direction. If you hold the magnet with its south pole facing the coil and repeat the above steps, the deflections are again observed, but are reversed.
So here you can see, as the polarity of the magnet was reversed, first the north pole was taken, so and the second time the south pole was moved inside the coil. So that time when the polarity of the magnet was changed, the direction of the induced current also had been changed. So it depends on the polarity of the magnet which we are changing. Okay.
Similarly, motion of the coil itself also produces deflections in the galvanometer when the magnet is kept stationary. Do you observe any deflection when you just hold the magnet stationary near the coil at rest? No. A relative motion of a magnet and a coil induces the current in the coil. The current produced by a relative motion of the coil or the magnet is called an induced current and is said to be set up by an induced electromotive force, EMF. The production of an induced EMF in a coil in a closed circuit by the relative motion of a magnet and its coil is called the phenomenon of electromagnetic induction.
Yes, Hope you have understood about electromagnetic induction, how the current is induced in the conductor when kept in a magnetic field, right? So you have understood about electromagnetic induction. So let us continue the topic in the next class. Thank you. If you have any doubts, you can ask me.